So in this particular video, I will show you how to attack problems where there are multiple point masses, and then it asks for whether the angular momentum of each or the total angular momentum of the whole entire system. So here, there are two parts. Part A asks you to find the angular momentum of each of the particle. And in the schematic, there are 4 point masses, M1, M2, M3, and M4. And then part B asks you what is the total angular momentum of the system. So to do part B, we have to first find part A individually first and then just sum everything up. So if you want to take a second, pause the video, write all these masses out given in the problem and all the velocity given in IJ notation. All right, so let's go ahead and get started. So I'll show you how to find the angular momentum of each particle in the order based on subscript. So here is the first one, which is M1. To find the angular momentum of a point mass, again, we reference this particular function where angular momentum is the coefficient of a point mass times r that is perpendicular to the linear momentum vector. Um, so we can go ahead and break up P into mv. The function for linear momentum is mass times the linear velocity. And then from there, we can look at the diagram here. So all we have to do is find r, and that's pretty much it for this one because the velocity is all given in the statement. Okay. So to the left of the diagram here, I have a red arrow going from the origin, aka the reference point in this particular problem, and that is a distance of 2 meters above the horizontal axis, and there's M1. And then from here, we can see that V1 is already perpendicular to R. So for this first mass, pretty straightforward, just plug and chug, okay? So what I have here to the right or in the middle of the screen, I just kind of move everything. So to separate it individually, here is our vector R, which is in the y-axis, and then V1 is already given in the x direction, and x and y are perpendicular already. So all we have to do is just plug in chug. C is a 1 for a point mass. The R value here would be a 2. According to the diagram, it is a distance of 2 meters above the x-axis. And then M is given in the statement here, up here where my cursor is. That is 0.1 kilogram. It's already in kilograms, so we don't have to convert anything. And then the velocity of V1 is straight to the right, and that is given here in the statement. It says V1 is equal to 2I, aka in the x direction. So all we have to do is calculator work, and then you do calculator work, you'll get a value of 0.4 with the proper units, of course, for angular momentum. And in this case, I put clockwise just to help you visualize how the system is going to rotate. So if you can visualize, again, the pivot point is going to be where the origin is at the beginning of the position vector, which is the red arrow. So visualize a dot there. So if you were to pull this red arrow to the right, which way will it rotate? In my world, it rotates clockwise. So this is just to help you visualize clockwise, counterclockwise, and then also ready into the board or out of the board. So for you to do these types of problems correctly and provide the right direction, if you can visualize taking a screwdriver and rotating the screwdriver in this direction, in the clockwise direction, the screw should be heading away from you into the board. So in this case, the K notation would be into the board. Okay, so I've provided 2 options for you. You can think of clockwise, or on a more technical term, it would be into the board. So the K vector would be pointing into the screen as you are watching this. So if hopefully you can visualize the screwdriver being drive into a piece of wood. Okay, so it's going to go away from you, aka into the board. All right, so other than that, that is that for that. And you notice down here, I have the answer for angular momentum as a negative quantity here because negative just indicate the direction, and that ends in the k direction. So negative k would imply that the vector is going away from us into the board. All right, so that takes care of M1. Let's go ahead and get the M2. M2 is at the bottom of the screen in the 4th quadrant there. So just like the last process, let's go ahead and draw our vector out from the origin all the way to the point mass. That's your vector R. But you notice here the distance here is 2 down and also 2 to the right. So it forms a 45 degrees angle. And then I'd like to point this out. Hopefully, as you're doing these types of problems, you can kind of pay attention to the details. V2 here is given as 3x and negative 3y, which is also 45 degrees. So I'll show you how to do this formally for M2. But you notice because the distance here is 2 over and then 2 down, which is 45 degrees. However, your velocity vector is 3 to the right and 3 down, which implies that these two vectors are parallel to each other, aka 45 degrees measure beneath the horizontal axis. So therefore, because they're parallel, they will actually generate no angular momentum. But I'll show you how to do it officially for this one. All right, so let's go ahead and split R into Rx and Ry as usual. This will help you kind of focus your attention on what it is that you need. And let's go ahead and break up V2 into the Vx and Vy component as well. So Vx is going to be V2x is going to point to the right, and then V2y is going to point down. Again, it's in the fourth quadrant. So from there, I clean up the work for you a little bit on the right side of the screen here. So angular momentum is CR/mv. In this case, R, what we need for the first component is Rx. But if we're going to use Rx, then we need to use Vy. And then Vy in this particular point mass of M2 is given the statement of -3. However, I'm just going to use the magnitude here, the speed here, because I like to think of it in terms of how it rotates. So whether I need to add or subtract angular momentum is based on how it rotates clockwise or counterclockwise or into the board or out of the board. So you notice here I just use the speed here. And then just plug and chug. C is 1 again. R in this case is given as 2 in this diagram. It starts from the origin, it ends there. And then if you just follow the grid here, it's 2 to the right. And then the mass is given in the statement. It says M2 is 0.2 kilogram. And then your velocity here is going to be a 3. Again, I'm just going to use 3 instead of -3 because I know it's going to rotate clockwise. Again, here's your pivot. I put my pivot at the end of where the RX starts, and then I would visualize if I were to pull down on that red arrow, it will rotate clockwise. So in this case, I've indicated clockwise in red here just to keep track of which way the object's rotating. If you want to do IJK notation, again, rotating the object clockwise in this case would be into the page. The K vector would be a -K because it's into the page. So if you, again, visualize your hand holding a screwdriver, and you rotate the handle clockwise, the screw should be going into the board away from you. Okay, so that'd be -K. All right, and then we can do the same. We took care of Rx and Vy already, so now it's time to take care of Ry and Vx. Ry in this case, according to the diagram, is just 2 down. Again, but you notice here I'm just using just the magnitude of everything. And then Vx is 3 from this particular chart up here. In the statement, it says Vx is 3i, so that's the 3. And then again, Ry and V2x is already perpendicular, so we would just have to plug and chuck here. C for point mass is 1, R is 2, mass is 0.2, and then V is also 3 for this particular problem because it gives us a nice dimension of 3x and 3 in the y direction. Okay. So calculated work is going to yield the same outcome. It's the same magnitude as the previous component. But you notice here in this one, it is going to rotate counterclockwise. So here's the pivot where my cursor is. If you were to take your hand and pull this red arrow in the direction of V2x, it's going to cause the system to rotate counterclockwise. So right away, we notice we have the same magnitude up here. That's clockwise, but we also have the same magnitude of 1.2 here in the counterclockwise direction. So really, if we sum it up, the two will cancel out, and that'll leave us with 0. Okay, so in this particular problem, based on how the velocity for object 2 is drawn, it parallels the r value because, again, this is a distance of 2 and down 2, which is 45 degrees. But the velocity vector given in the statement up here is also a 3 by 3, which is also 45 degrees. So the vector r and v2 is parallel. So ultimately, it generates no angular momentum. No angular momentum is produced by M2's direction. All right, so keep that in mind. And then let's do M3. All right, so M3 is in the second quadrant here, and it has a velocity vector pointing downward, and then there's some distance away from R. So let's go ahead and set this stuff up again. We need R and we need V that are perpendicular. So I drew my R vector from origin to where the point mass is. And this stuff is pretty easy to do. Split this up into components. We need Rx and Ry. In this case, why we can draw Ry, we don't really need Ry because if you notice here, V3 is along the y direction. you don't want parallel, you want perpendicular, so you need to use Rx up here. So if you watch the screen, Rx in this case is there on the screen, and then V3 I connected, and that's perpendicular. So in this case, we would just multiply everything. Again, C is 1, R is 3, because from the origin, you go 3 to the left, and then 1 up. So we need just the horizontal R, which is a distance of 3. Okay. And then mass for M3 is given up in the statement as zero point 0.3, and then V is 1.5, because in the problem up here where my cursor is, it says V3 is negative 1.5. But you notice here, again, I'm just using 1.5 just as speed, but then whether it rotates clockwise, counterclockwise, into the board, out of the board, I can figure that stuff pretty easily. So in this case, it would produce a counterclockwise rotation. So here's my pivot where my cursor would be. If you reference that, and there's the R. If you pull down on the end of the red arrow, it would generate a counterclockwise rotation. In this case, if you think about it, it would be coming out at you. Okay, so the K vector is going to come out at you. So again, if you visualize a screwdriver and you rotate it counterclockwise, okay, the screw is going to be coming back out at you. So that's how you loosen a screw. So therefore, this is counterclockwise, or AKA in the positive K axis. So positive K hat would be coming out at your face right now. So it's coming out of the screen or out of the page, however you want to say. All right. Other than that, the magnitude is 1.35 K, and that's that. Okay. And let's move on to M4. Okay. So here's M4. M4 here, if you notice, the mass lies on the horizontal axis, aka the x-axis, but then the velocity here also lies on the horizontal axis, which runs right through the axis of rotation, or the reference point. So if you watch my cursor, if I extend that green velocity V4 arrow, it'll run right through the reference point. So while there is a V, there is no R, and if there's no R, then it generates no angular momentum. So I went ahead and put a box around that, and I just call it whack. Okay. So while there is a mass, pay attention to how the velocity vector is drawn and whether it's perpendicular to the reference point or not. In this case, it is not. It is parallel, and it runs right through the origin. So it generates no angular momentum. So really, of the 4 point masses, we only have 2 that contributed to angular momentum. That would be M1 and M3. So all we have to do is really sum it up. So here for M3, the angular momentum is 1.35 in the positive K. And then for M1, that was a negative 0.4 K. So adding them or taking the difference, however you want to do it, would yield an answer of 0.95 K. And again, in this case, positive K would imply that the vector for angular momentum is coming out of the board at you. Okay. So, or in this case, it would be counterclockwise if that's acceptable. Okay. Other than that, there is your outcome. I hope that helps. If you need to, watch the video a little slow and watch where all the numbers come from. Stay nerdy. Don't be whack.